Hey, afternoon, everybody, and welcome to the How Do You Know show. I'm on my own this week, and still kind of recovering from my cold. So if my voice cracks a little bit, hope you'll excuse me. And good to be back. Last week I missed classes and everything, but it's a great time for you if you are an astronomer. Uh, Tonight, after our show is over, here at the Barth Ranch in the Ozarks, we're having astronomy lab tonight for my Astronomy for Educators students. And we're going to be looking at moons of Jupiter and moons of Saturn. And if you check out my book, Star Mentor, you will find activities in there to help you track and identify moons of Saturn, moons of Jupiter, how to accurately sketch Saturn at the eyepiece. It's easier than you think. And those resources are available. Springer.com has downloadable resources, and the book, of course, is on Amazon and other quality booksellers. Well, apart from our astronomy weekend, how many of you got out on the International Observe the Moon Day last weekend? I did. I got out and was observing the moon, and I'm always delighted to watch sunrise in the craters along the terminator. You can see this absolutely inky black crater and a pinpoint or two of light in the center where the tops of the central mounts, these big craters have central mountains that rise sometimes 3, 4, 5 kilometers out of the basin. And these peaks, these small little peaks, catch the sunlight before the rest of the mountain in the center does. The whole crater basin is in shadow. And if you get a chance to get out and observe, we're at first quarter moon tonight. And this whole week will be a great time to observe these sort of effects. Keep in mind that when we look at the terminator, the boundary line between the light and the dark on the moon, we're seeing sunrise during waxing moon. And if you watch it during waning moon, which is up in the evening or early morning, you're seeing sunset. So that's very exciting. Sorry? Yes, indeed. Um, and as usual, I don't have a copy here to hand. I usually do. Maybe Paul can put up an image for me. There we go. Yeah, that's the Star Mentor book. And we're starting to see more reviews online, and I'm thrilled, and thank you very much. I very much appreciate those of you who've supported this program and my work by purchasing Star Mentor. The previous book, which is Astronomy for Educators, that's now in over 80, it's almost 8,400 schools, Paul. That's in over 60 countries, and we're serving something crazy like 300,000 or 400,000 students a year, which is just amazing. The Star Mentor is the civilians Astronomy for Educators. It's a whole series of activities that are derived from my work as a teacher of astronomy for many decades, and really have designed it to be a self-teaching guide. So you can take small telescope and binocular out and learn how to use them, how to read the sky, how to use a star map. And so many of us purchase a telescope and we take our first look at the moon or at Jupiter, and then we sort of say, but what now? Is there nothing more? And of course, there's whole worlds awaiting. But the Star Mentor book will help you find your way and learn to master your brand new telescope. And if you're an old hand, I'm hoping that these activities will show you something new and exciting with an instrument that you've long fallen in love with. So excited about that. That's available on Amazon. And if you want to support the Explore Live program with Kent Martz, which is on weekly, they usually put the Star Mentor book in the carousel there, and you can support not only me, but the Explore Live program in that way. And we appreciate you. Always happy to take your questions, either about the book or about the program, at astronomyforeducators@gmail.com. If you can see the little waggy tail in the background behind me, that's my buddy Parker, who's here with me. Anyway, so other fun stuff that's in the news, Paul. I put this on, and people say, "Well, what does this have to do with astronomy?" My wife looked at me and says, "Can you connect the dots for me here?" And scientists have calculated the total number of ants on Earth at any given time as 20 quadrillion, which is just ridiculous. It's a 2 followed by it's like 20 zeros. It's an amazing number. 2,000 ants on Earth for every star in the Milky Way. You know, we worry about having moving towards 10 billion human beings. For ants, that's a neighborhood. That's not a global issue. That's a neighborhood. It's stunning, and I've heard science fiction authors argue whether or not ant colonies should be considered a diversified intelligence. In other words, they do very clever things as a group, but as an individual, not so much. So that's really kind of interesting. The other science news that has been just stunning, and of course, this occurred on the week we were not together. It's kind of like, of course, naturally. The DART test, the double asteroid redirection test. And this was really brilliant. NASA went out and found an asteroid with a little tiny asteroid moon. And Dimorphos was the little moon. And they fired a spacecraft at it, which was basically to act like a dart, a kinetic impact device. It was like a bullet or an arrow. And their idea with this little test, they wanted to make sure it was safe. So they hit it head on into its orbital path so it would slow down and slip into a tighter orbit around the main asteroid. Dimorphos and Didymus, and I'm not sure if I'm saying those correctly, so you'll forgive me. But we did. We launched this spacecraft 7 million miles away. Whack, we hit it. We changed the orbit substantially. And I think we're going to, oh yes, DART was cool to watch. There have been some very exciting videos from NASA, and some amateurs on YouTube have gone ahead and collected together these videos, these images, and put them in as a video. And they were taking pictures up to a fraction of a second before the impact. So you're seeing this and you're thinking, oh my gosh, it's kind of like watching the train come down while your car is stalled on the tracks, just getting closer. But they also launched a little CubeSat to watch from farther away, where it would be safe. And this was very exciting stuff. And we're going to do a whole program on DART next week, and it will be very exciting. So let's go back into our two-part topic. And we talked about this 2 weeks ago. We talked about what's a theory and can we prove a theory? And how do we work with Einstein's theory and testing them? As we went over last time, we figured out that a theory is not something you can prove correct. You would have to have all the data all the time, forever, in the past, into the future. It's not a doable thing. Theories can be falsified, but not proved true. And so the things you hear when you start talking about the theory of relativity, well, why do they still call it a theory? Hasn't anyone proved it true yet? And wouldn't it be the law of relativity by now if it was any good? After all, it wasn't too long after Newton's work was published that they were calling it the universal law of gravitation. And so as we learn more about facts and hypotheses and theories, we realize that we cannot prove a theory true. We can just falsify it. And indeed, over a century of trying, no one's falsified Einstein yet. So we can test a theory, though. We can test a theory. And I remind you, the whole reason Albert Einstein is famous, really, he did many brilliant things through his lifetime. He won a Nobel Prize. It was not for relativity. The Nobel Committee never considered it sufficiently well tested during his lifetime, and you can't get one after you're dead. But his Nobel Prize was for photoelectric effect, which was evidence in support of the quantum theory, which is kind of weird. People think of quantum theory as being post-relativity, but it's actually not. And this theory of relativity, the special theory of relativity, which is about the speed of light. Einstein hated that name, by the way. And the general theory of relativity came out 10 years later, 1915. So these two theories have been with us now for more than a century. And people have been trying to put a dent in them in all that time. After all, Einstein is famous because he is the first person in 3.5 centuries to do any significant modification to the work of Isaac Newton and his universal theory of gravitation. So let's talk about these two theories, because there's two. And they're both referred to as theory of relativity, which, as I mentioned, Einstein really hated that. What we call the special theory of relativity deals with what Einstein referred to as the principle of invariance. And he wanted to call it invariance theory, but the other name caught on, and it's kind of like, well, now that everybody's calling it that and it's kind of internet famous, he couldn't really change it. It was kind of, the name for relativity theory was kind of crowdsourced. It's what other people were calling it as they discussed it. And Einstein wasn't in a situation where he could get it changed. But the main idea of special relativity is that the speed of light never changes. Now, that's an interesting thing. And if we think about the speed of light, let's think about, if we're talking about, the speed of an asteroid. Look, here's one now. If you think about the speed of anything, be it a football, an asteroid, a bullet, it doesn't matter. How we measure that speed makes a difference. If the two of us, the classic thought experiment, or Gedankenexperiment, as Einstein might have said, if the two of us are standing on a flatbed railroad car, and the train is in motion at 10 kilometers per hour, and we're tossing a baseball back and forth at 25 kilometers an hour, I will measure the speed of the baseball as 25 kilometers when you throw it towards me. Let's say Paul and I are on the train, and Paul is in the back of the car. I'm in the front. So he's throwing it in the same direction the train's moving, and I'm throwing it against the train's motion. Well, if someone on the side of the train tracks is measuring, when Paul throws the ball forward in the direction of the train's motion, someone from the side measuring that will say, oh, the train's moving 10 miles an hour. Paul threw the ball at 25 miles an hour. The combined speed of the ball, as someone on the side of the tracks would measure it with a radar gun, 35 miles an hour. On the other hand, if the train's in motion and I'm throwing towards the back of the car against the train's motion, it's then subtracted. So someone with a radar gun at the side of the tracks would measure my 25 mile an hour pitch minus 10 miles an hour. They would say, oh, I was throwing the ball backwards at only 15. And this all kind of makes sense if you think about it. But Einstein said if we try the same trick with flashlights or lasers, that no matter who is standing where, how the train's in motion or how you're in motion, you're always going to measure the speed of the laser beam as c, the speed of light, It is invariant and it never changes. Now, the reasons for this invariance that Einstein advanced, I'm not going to go into that today. You can go really deep down the rabbit hole very quickly when you talk about special relativity, and maybe if people are interested, put something in the comments. And if you'd like to see a whole program on special relativity or general relativity, we can do that. But Einstein said there's this amazing thing. The speed of light doesn't change, no matter who's measuring it, how they're moving, or how the light source is moving toward or away from you. Think of that if you're measuring stars in the Milky Way. And we say, oh, if a star is moving toward us, the speed of light is c. If the star is moving away from us, the speed of light is c. And if we're looking at a galaxy, which is in rotation, and we think, let's say Andromeda. I was out the other night looking at Andromeda. One side of Andromeda, because we see it almost edge on, one side is rotating toward me, the other side is rotating away from me. If I measure the speed of light from stars on either side of the galaxy or the central bulge, I get the exact same number. Now, people will immediately say, oh, but Dr. Barth, we've heard of redshift, we've heard of blue shift. Isn't that a change of speed? No, it isn't. It's a change of energy. It takes more energy to pump photons up toward the blue end of the spectrum. Down towards the red end of the spectrum, they have less energy, which is why we use a red light when we're out reading a map at night at the telescope eyepiece, because that low energy red light will not activate our color vision. It will not damage our dark adaptation. Whereas if we're using a blue light from a flashlight or a cell phone, that's going to change the way our retinas perceive light and ruin your night vision. Well, so this idea that the speed of starlight is invariant, but the frequency or wavelength, both ways of measuring the energy of a photon, that does change. If the side of Andromeda is rotating toward you, the light from those stars will be blue shifted. They will have additional energy because the star that's emitting that light is moving toward you. The opposite side of the galaxy will be red shifted because that star emitting that light is moving away from you. And so, yes, the energy changes, the speed does not. Matter of fact, one of the proofs that the speed doesn't change is that the frequency and wavelength does. So this idea of the Doppler shift of light is really an interesting idea, and it fits in very nicely with Einstein's relativity theory. And it turns out the very first test of the special theory of relativity, the invariance principle, as Einstein referred to it, was actually something called the Michelson-Morley experiment, which is from 1880, which predates the special theory of relativity by a quarter century. At that time, the prevailing theory was called the ether theory. This AE combined diphthong letter, AETHER, ether theory. And the ether was supposed to be this very thin, very rigid medium that light traveled through. We think of ocean waves as traveling through the ocean. Earthquake waves travel through the interior of the earth. There's an ocean wave, something has to be waving. That medium that is waving is the ocean. And people said, well, we know light is a wave. It must be the same. So there must be this ether, this substance through which light travels. Otherwise, how could light travel in a vacuum? Because we know ocean waves stop at the shore. Earthquake waves don't propagate out into space because there's nothing there to jiggle in an earthquake. Well, then how can the light travel if it doesn't have a medium? And so it must be the ether. Well, Michelson and Morley said, oh, as the Earth orbits the sun and as it spins on its axis, if we try to check the speed of light in the direction the Earth is traveling, we should find out that the speed of light is slower because it's like plowing into the direction we're traveling. On the other hand, going the other way, it should be faster. And so Michelson and Morley said this will be a definitive test for the existence of the ether. Because depending on the way the light wave is moving through the ether, we should see that it's traveling faster or slower because the ether is thought to be at rest. It's certainly, the ether couldn't be dragging around attached to the Earth. That's like the old geocentric theory, and people had discarded that idea long enough. You see this relevance between my thought experiment with the train and the two baseballs and the Michelson-Morley effect with light traveling through the ether. The only thing is, they found no change in speed. No matter how they oriented their experiment, and they tried it in perpendicular directions in the X, Y, and Z axis, and they measured the light speed at the same time, and they did it independently, and they did it together, and no matter how they did it, they could find no change in the speed of light. And the answer that Michelson and Morley came to was simply that, well, if the ether was a real physical thing, it would affect the speed of a wave traveling through it. If you think about it, again, another water analogy, think of a riverboat and traveling down a river. And if the river boat is traveling downstream, that's going to affect the speed of the waves thrown by the wake of the boat as they move down the river and toward shore. Same way, if the river boat is moving upstream, it'll have the opposite effect because the waves are now fighting the current. So does the river current add to the speed of the wave or detract from it? And by this, even if we didn't understand water, we could say, oh, water really exists because we can see its effect on the wave. On the other hand, with light, there's no effect at all. And Michelson and Morley said, well, there's no effect at all because it doesn't exist. And so this experiment, which is done in physics programs all over the world, they recreate the Michelson-Morley test with more modern methods. They use lasers and other things that Michelson and Morley did not have. But it's a relatively easy tabletop experiment to do in any high school or college physics lab. And you can show the ether doesn't exist. Well, this was kind of a point for Einstein. The idea that the speed of light doesn't change no matter how you're moving. And in this case, the moving platform was not a train or an automobile or a horse and cart. It was the Earth itself. So very reliable, very well known, speed precisely known, and it had no effect on the speed of light whatsoever. So the general relativity theory comes 10 years later, and general relativity deals with gravitation. Like Newton's idea of universal gravitation, which said things like all planetary and stellar masses function as if all the mass is at a point in the center, and every object has a positive gravitational attraction to every other, and the idea that the gravitational strength decreases with the square of distance, the inverse square law. The thing Newton didn't propose is, how does gravity work? What's the mechanism? And Newton shied away from this. His famous hypothesis non fingo, I hold no hypotheses. He basically said, I'm just telling you what happened. I'm not telling you how it works, and I'm not even going to make a guess. Well, Einstein comes along 3.5 centuries later, and he says, you know what? Yeah, I can show you how it works and what the mechanism is. And this is the idea of space-time. And Einstein says gravity is the space-time well. We've all seen these diagrams where the flat surface curves in. You may have the ideal experiment is the rubber sheet and the bowling ball. I've done experiments like this with my students. I do them every year. We have a wooden frame with a piece of spandex type knitted fabric stretched over the top, and we put billiard balls on it, and they make a dimple in the fabric, and you roll a marble across and it curves. This great stuff. Basically, Einstein said it's the curvature of space-time. John Wheeler, student of Einstein, put it much more succinctly. He said, mass tells space-time how to curve, and the curvature of space-time tells mass how to move. And so this idea that the special and the general theory talk about light and gravity, and together they come up, it was a revolution in physics. So why are we still testing this a century and some later? 115, 125 years later, depending on what part of the theory you're talking about. Why is this so hard? Well, it turns out that if you wanted to fly a rocket from here to Mars, both theories will give you the same answer. Newton's theory is a lot easier to work with mathematically. But both theories give you functionally the identical answer. The answers for Einstein's theory and Newton's theory only diverge under very special circumstances. Either there is a tremendous amount of mass involved. Planetary masses don't really get it. You need stellar size masses or bigger. Things of great density also work because the gravitational field is so strong. So things like neutron stars and black holes, even if they're relatively small, these two start to show a divergence between what Newton predicts and Einstein predicts. The second thing is if you can have great velocities approaching the speed of light. You realize that the Apollo astronauts, the New Horizons spacecraft, which is the fastest thing, travels only a tiny fraction of the speed of light. It's a really formidable challenge to find ways to measure the changes or the differences between Einstein and Newton's theory, because if we can't just lasso a black hole or get a spacecraft to go say, 0.7 light speed, like something out of Star Wars or Star Trek, then the alternative is we have to measure the very tiny differences predicted between the two theories. So either we have to have clocks that can measure a billionth of a second, or other devices that can measure things very, very precisely, or we have to look out into deep space where we see things like galaxy clusters, black holes, neutron stars, and we have to measure the effects of relativity. It turns out that satellites in low Earth orbit, 100, 200 kilometers up, these satellites move fast enough that, yes, indeed, 25,000 kilometers an hour, give or take. And yes, they move fast enough that the difference between Newton and Einstein is significant. How do we know this? Well, I have GPS on my phone. You probably have it on your phone and in your car as well. And it turns out if we don't use Einstein's theory to account for the high-speed motion of the satellite, we couldn't have GPS that was more accurate than about, say, 250 meters, quarter of a kilometer. And if you're going to say, take a left on Fleet Street in 0.6 kilometers or 0.25 miles, well, guess what, friends? If you're not accurate to more than a tenth of a mile or a quarter of a kilometer, GPS for a street map isn't going to work. So you, I, your Toyota or Volvo or whatever, Ford, They all use Einstein's theory of relativity every single day. If you have Google Maps, if you have onboard navigation in your automobile, guess what? You're using Einstein's theory of relativity every day, which is kind of a smack in the face to people who do little TikTok videos. I took algebra and I realized I would never use math again in my life. No, you do. You just don't recognize it. So, how do we test this? Einstein himself proposed 3 tests for relativity. The first one involved the orbit of Mercury. And this was a problem that dates back to the 1700s and the great French astronomer Urbain Le Verrier, who, with John Couch Adams and Johann Galle, the 3 of them teamed up to discover the planet Neptune. And Le Verrier was an astronomer's astronomer. He was a tremendously skilled mathematician and a very skilled observer. And he was into measuring things to the last possible decimal place. And he confirmed, others had detected this before him, but he confirmed that in fact, the ellipse of Mercury's orbit. See if I can demonstrate this for you. This is an easy thing to demonstrate with clay. Here we have an ellipse. And if I take a look at this, friends, and the ellipse has an axis to it. So it has a place where there's a perihelion, where Mercury is pretty close to the sun, and an aphelion. And it turned out that the perihelion of Mercury, instead of staying where it should, was advancing a tiny fraction of a degree per century. This was a very small effect. The fact that observers in the 1700s were able to see this at all, I bow down to their mad astronomy skills. These folks were the bomb. They really were high precision astronomers. And Le Verrier said, oh, I know what this is. Somehow orbiting around the sun, what's messing up Mercury's orbit? There has to be another small planet. And it's probably inside Mercury's orbit. And it's just close enough and it's just big enough that it's having this tiny little gravitational tug and it's messing things up. They called this planet Vulcan. And people searched for Vulcan for more than 100 years. If you want to know more about that, one of our books of the week, we try to have one of these every week. This has become popular with our Thomas Levinson, The Hunt for Vulcan. This is almost like a detective story. Reads like a detective novel. It's wonderful. It's an easy read, and this would be digestible. Anybody with a high school education is going to follow this just fine. Younger kids could follow this, and it's exciting, it's a fast read, and we read about these people who were all hunting for something they were sure was there, but it actually wasn't. This is kind of the whole hunt for the ether again. And this is the first time people have predicted things that have turned out not to be true or not to be there. So people search for this. The second test Einstein proposed, he said, well, warped space-time should cause light to be deflected. So he said, if we looked at a solar eclipse, we should be able to see that, in fact, light will curve around the sun. It'll be a very small effect. Newton predicted a small effect too. Einstein's effect was twice as big. So Einstein said, here's a clear predictor. And Einstein said, we should be able to photograph stars near the limb of the sun during an eclipse, and we should be able to see and photograph and measure that tiny little deviation. This is an extremely difficult technical challenge. People were still trying to repeat it into the 1970s, and it has defeated almost every scientific team that ever attempted it. The one fellow that actually got it right and showed the effect Einstein was predicting was the team of Arthur Eddington and Frank Dyson. No relation to the vacuum cleaner magnet. This book, No Shadow of a Doubt, by my friend and colleague Daniel Kennefic, who's a professor of physics here at the University of Arkansas. He's also an Einstein scholar. And he's written a couple of lovely books on gravitational waves. And this one in particular was about the quest for Eddington and Dyson to prove Einstein's theory. And I use that with a grain of salt. What they were looking for was evidence that Einstein's theory was correct and that Einstein did successfully modify Newton. And these two scientists set out, and Eddington went to the island of Principe, which is off the western coast of Africa, and Dyson went to the interior of South America, what is now Brazil, if I'm remembering correctly. And the two of them took along telescopes and equipment to measure. Remember, at this time, 1919, they didn't have the capacity for highly accurate electric computerized tracking drives, so they were doing all sorts of things. And these fellows went, and Dyson did not get a good photograph, but Eddington did. And he came back and he announced this to the world. And this is the experiment that made Einstein famous overnight. And I believe it was Eddington who made the quip that Dr. Einstein has written a book for 12 people because nobody else will understand it. In fact, lots of us understand it now. And Einstein's own book on relativity is quite readable. And you can still find that on Amazon and other booksellers today. So the third test is that Einstein said, crawling out of a gravity well should cost you energy. Again, if we think of a more mundane, let's take a baseball and throw it up in the air. Well, we see that as we throw the baseball, as it goes higher, it loses speed, and finally it loses enough energy and it falls back. But even if we're using a rocket to send a satellite off to whack an asteroid, it turns out that as we climb through the atmosphere, we have to keep putting rocket power in. Otherwise, our rocket will slow down. It costs energy to get out of a gravitational well. And Einstein said, we should see a gravitational redshift. Light, as it leaves a massive star, should be redder than it should be because the gravity changes the frequency of light as it leaves. So it turns out these three tests were really quite exciting. The gravitational deflection of light around the sun during eclipse, that was done in 1919. The orbit of Mercury, Einstein simply compared his own paper and pencil calculations to the very accurate observations being made by astronomers. He found that was working sometime in 1908 or 1909. And by 1919, about a decade later, and several years after this general theory was announced, we have Dyson and Eddington who find out Einstein was correct in his predictions of how light should move around a massive star. And this makes Einstein kind of overnight famous. And Einstein himself was kind of uncomfortable with this. Keep in mind that Einstein was not your typical hero. He was a rebel, a Jewish man who was born in Germany, and he didn't like the way his country was going politically. So he left and gave up his Jewish citizenship and became a Swiss. And then during World War II, the Swiss were cooperating with both sides, the Allies and the Nazis. He's like, no. And he leaves Switzerland and he goes to the United States and becomes an American citizen and continues to work here for the rest of his life. It turns out this gravitational Doppler shift, Einstein said we should see both things. We should see a gravitational redshift of light leaving a massive star. We should also see a gravitational blue shift of light falling toward a massive star. And it turns out, again, the difference between Newton and Einstein is very, very small. And so to measure the difference, because Newton also predicts red and blue shifts, and to measure the difference requires a really extremely high level of precision. And it turns out that this entire small effect problem plagues people who seek to test Einstein's theory to this very day. And so, again, if you want to measure this change in the frequency of light, you need an ultra-precise spectrograph. If you want to measure the change in a clock, which is predicted by special relativity, you need an atomic clock, something that will keep time to a billionth of a second. Turns out this gravitational redshift wasn't done until 1954, the year before Einstein himself died. And it was done by a fellow named Popper. And I've tried to find information on Popper. I do not think it was the Karl Popper we talk about all the time. It was within his lifetime. The timing would have been right. But I think it was a different fellow, because Karl Popper, I do not think of him at all as an experimental astronomer or astrophysicist. But this was done first by a fellow named Popper in, so it's a fellow, I don't know, the time frame would suggest it, in 1954. So special relativity, the one which works on clocks and the speed of light, special relativity says three odd things. When you're moving really, really fast, clocks slow down relative to someone at rest. In other words, the clock in a very fast rocket ship will tick more slowly than the clock of an observer who's standing still and watching the rocket whoosh by. The second one it says is that the length only in the direction of motion will shrink. So if we are standing and watching a rocket approach, that rocket will appear shrunken in the direction of motion compared to when it's just perpendicular to us and going past, it will appear as at normal length, and then as we look at it. So length changes, and the third one is that mass increases. Well, all these effects are really tiny because it turns out it's a ratio between your speed and the speed of light. And when you talk about any velocity compared to 300,000 kilometers per second, well, gee, guess what? That ratio is pretty ridiculously small at regular, like automobile rocket ship sort of speeds. We didn't test this clock effect on fast objects until the Apollo era. NASA had the very happy idea that if we put a very accurate atomic clock aboard an Apollo command module, and it flies at very high speed to the moon and orbits the moon at high speed for several days, and then it flies back, it should show a significant deviation with a twin clock stationary on Earth at NASA headquarters. Both of them started at the same time, and then the one clock is put aboard the Apollo spacecraft, and they were indeed able to show that Einstein's theory correctly predicts the deviance, the differential between the clock in flight and the clock on the ground. Let's talk about other tests of Einstein's ideas. One of the biggest ones that did not come from Einstein himself was from Edwin Hubble, the expansion of the universe. Einstein's theory, his field equations, there are 10 of them, basically indicated that the universe could, the universe could be contracting, or in a very special case, the universe could be stationary. This is kind of like the idea of an orbit. Most of the time we say, oh, Kepler was right, orbits are elliptical. It's not that orbits cannot be perfectly circular. It's that this is a special case, and any little bump or deviation will knock it back into an ellipse again. Well, Einstein really looked at this, and he had a lot of problems with it philosophically, emotionally, intellectually. And so he tweaked his equations and he introduced the cosmological constant that would basically make the universe stationary. He said, oh, if you multiply by this, it turns out everything is unchanging. Well, Hubble then went and started looking at galaxies and redshifts, and you know the story. He found that almost every galaxy was redshifting. They're all moving away from us. If they're all moving away, with very, very few exceptions, the idea is perhaps the universe is expanding. And that idea has been tested many times over the decades. And so Hubble's idea that the universe quite neatly fit one of the predictions of Einstein's theory of relativity was a major coup for Einstein, even though he didn't like the result. More recently, there's something we call the Einstein Ring. This is also known as Einstein's telescope. It turns out that if you want to see something very, very far away, we do this with telescopes all the time. We take a refractor with a lens or a reflector with a mirror, and we gather a lot more light than our eye can and use it to make things brighter, which are far away and faint. The idea was if you had a very distant galaxy or star, and you had a very massive object, neutron star, black hole, galaxy, galaxy cluster, and if the massive object was halfway between the Earth, if we have this massive object, that light rays that were traveling and would normally miss us, the gravity would redirect them and they would reconverge. For this to work, excuse me, you have to have some very special circumstances. The massive object has to be at exactly the right distance. It has to be exactly in a line between us and the object we want to see. And it turns out that the light from the object is not well focused into a point, but oftentimes the gravitational effect will smear the image of a galaxy into an arc, or in a perfect situation with perfect alignment, into a ring. Now, we've seen Einstein arcs for many years, decades. The Webb telescope, hooray for Webb, recently discovered an almost perfect Einstein ring, where a galaxy was hiding behind a massive galaxy cluster between the Earth and the galaxy, which was far too far away and far too faint to be seen in any normal way. And this Einstein's telescope gravitational lensing refocused that light and made it possible for us to see. And very clever fellows and folks much smarter than yours truly figure out how to do the computer processing to take that ring or smeared arc image and process it back into what we would consider a normal focused telescopic image. So there we go. The next test is something that's just happened in the last decade, and that's gravitational waves. Einstein predicted that space-time is flexible. It's extraordinarily rigid. Think of a very, very rigid spring. It takes a huge mass to bend space-time significantly. If you want to think about it this way, and I've done this routinely for my astronomy and physics students. You take a small refrigerator magnet and a paper clip, and you go, oh, look. And the magnet is able to pick up the paper clip. And you go, wow, look at that. Isn't it amazing? And everybody says, so what? Every child has done this. Taken a magnet and picked up nails or paper clips or small pieces of metal until you start thinking, yeah, okay, but this little refrigerator magnet has conquered the gravitational pull of the entire planet Earth. And when you think about it that way, it's really, really astonishing. It tells you that the difference between gravity and magnetism is amazingly huge. 40 orders of magnitude, that number 10 to the 40 that occurs in lots of places, this is one of them. And so Einstein said if this fabric can be bent, if it acts like a spring, then it can also be a medium for waves. And so when we see things like stars exploding, massive stars or black holes or neutron stars colliding, this should create huge gravitational waves. And furthermore, Einstein predicted that when two small compact objects like two black holes or two neutron stars are orbiting each other, one of the ways that they will give off energy and so spiral in together is by creating gravitational waves. And you've probably seen, if you look up on YouTube and you say, oh, visualization of gravity waves, visualization of colliding neutron stars, you'll see one of these lovely videos. They've been made by ESA, NASA, many universities, independent, clever folks have done these. And you'll see these things spiraling in and the gravitational waves. Well, we said, oh, let's build a gravitational wave detector. And so the idea was we would have two bars that were perpendicular to each other, and one would be tugged and shrunk along its length by the gravity wave, the other would not. And so, oh, we can use these perpendicular bars as a telescope to tell us first to detect gravitational waves, first done in 2015. And then we can use them as a telescope. And later we have this program that's in space. The one on the Earth is called LIGO, the Laser Interferometer Gravitational Observatory. There's one that's called Virgo that's out in space. And in fact, we do much the same thing. And we're looking at the changes due to gravity waves. And so we've detected those. My friend Dan Kennefick has a book, and I'll feature that next week, about gravity waves. And he's quite the writer. I admire him very much. The latest test is called the Microscope Satellite. And you know how all these ESA and NASA folks do. Of course, it's an acronym. This one's in French. So I'm going to massacre this, guys. I don't speak French. I'm going to massacre this. Microscope Satellite a traîné compensé pour l'observation du principe d'équivalence. My apologies to all our French-speaking viewers today. I know I mucked that up horribly. Sorry. This is a French satellite. And what it does is it has two very precisely known masses in the satellite, and they're in free fall together. The principal equivalence says acceleration is the same as gravity. And so as these two objects orbit the Earth, we can measure their relative motion, and we can see if Einstein is in fact correct. And in fact, the Microscope Satellite people, they claim their results now show that the predictions of general relativity are accurate to a few parts in 1,000 trillion. That's nutty. That's absolutely insane. And they claim that if they can get better isolation of thermal effects, because guess what? Heat is actually vibration, right? You've heard that. Heat is actually kinetic energy at the atomic level. And so our friends at ESA say, oh, if we can get the thermal effects ironed out, get it cooled down to a few micro uh, degrees above absolute zero, they can improve their results by a factor of 100. Why would that be significant? Because in the last century and a quarter, no one has been able to find a working linkage between relativity and quantum theory, the two most successful scientific theories of 20th century physics. And they should be talking about the same thing, but when you do calculations based on quantum theory and then based on Einsteinian relativity, they just don't agree. And how do we account for this problem? Well, again, it's the small effect problem. Except between quantum theory and Einsteinian relativity, the differences are even much smaller than between Newtonian gravitation and Einsteinian gravitation. And so we need some really, really precise experiments so we can start disproving and going, ping, and knock some of these theories out of the arena. So that's where we are. We have just a few minutes left, so I'll ask Paul, do we have some exciting questions going on here? Any fun questions or comments tonight? I'm not seeing any of these on the board, and I'm not hearing Paul at this time. Maybe we'll assume I've taught you all to a standstill once again. Good.
Dr. Barth, we've
Yes,
got
sir.
some kind of mechanical electronic
Okay.
problem here, so we're working behind the scenes I can't say it, as hard as we can to keep the place from burning down.
Okay.
So hang on.
Our digital infrastructure has been sabotaged like the Nord gas pipeline. Oh, well.
I
You know
don't
what,
see
guys?
any questions, so
I'm sure there are some. Email those to me or to the show, and we'll take them up next week at the beginning of the show. But it is 5 o'clock. It's 5 o'clock here. Don't know about where you are. And it's not like the song is 5 o'clock somewhere. I need to go eat my dinner. And then in about an hour and a half, my students will be arriving for astronomy lab tonight, and we're going to go out observing Jupiter and Saturn and their moons, the Andromeda Galaxy, and other fun things. I hope you'll have a chance to use some clear skies this month, because the observing time for Saturn and Jupiter is prime in the early evening. Andromeda is now up in the early evening where we can observe it easily. Clear skies to you all. And thank you, everyone, for supporting the How Do You Know program and the Star Mentor book. This is Dr. Daniel Barth logging off, and we'll see you again next week. Bye-bye now.